Welcome, curious minds and sleepy thinkers. You've found a soft place to land where the questions are big and the pace is slow enough not to jolt you out of your pillow cocoon. Tonight, we're going to tiptoe into one of the most mysterious questions ever asked. What lies beyond the boundaries of our known universe? But don't worry, we'll take it slow. This isn't a race through equations. It's more like floating through a galaxy of ideas with a cup of chamomile tea. We will simply let our imaginations wander, allowing ourselves to be filled with the quiet, profound wonder of the cosmos. As we begin this journey, let go of the need for definitive answers and instead embrace the beauty of the unknown. We'll explore some of the most mind-bending concepts that scientists are contemplating, not as a lecture, but as a shared exploration of the great mysteries that surround us. Let's begin by grounding ourselves in what we think we know, or at least what our senses and our most advanced tools have shown us. Our universe, the one we can observe, is a sphere of perception. It's like being in a lighthouse on a calm, dark sea with our light beam extending out to a certain distance. Everything within that beam is what we call the observable universe, and it is vast, beyond all comprehension. Its diameter spans approximately 93 billion light-years, a number so enormous it loses all meaning. A light-year, as a reminder, is the distance light travels in a year, and nothing travels faster than light. A billion is 1,000 million. Just let that number echo for a moment, a quiet sound in the vastness of your mind. We are talking about a cosmic ocean so wide that our minds struggle to even form a picture of it. This immense expanse is not empty. It is home to an estimated 2 trillion galaxies, each one a swirling city of stars, gas, and dust. 2 trillion. Try to imagine it. Each galaxy is a masterpiece of light and gravity, and each one holds within it countless stars, many of which are surrounded by their own planets. The sheer size of this immense tapestry challenges our understanding of scale and distance, stretching the limits of human comprehension. To put it simply, we are a tiny, tiny speck on a tiny, tiny planet orbiting an average star in one of 2 trillion galaxies. The humbling scale of it all is one of the most beautiful and grounding truths we have. It's a gentle reminder of our smallness, and in that smallness, we find an invitation to wonder. The cosmic stage upon which all this drama unfolds also has a shape. For a long time, we didn't know what it was. Would it curve inward, like the surface of a sphere, or curve outward like a saddle? But the best evidence we have, based on the subtle patterns in the cosmic microwave background radiation, which we'll talk more about in a moment, suggests that on a large enough scale, the universe appears to be flat. But this flatness isn't like the two-dimensional surface of a sheet of paper. Instead, it's more like a vast three-dimensional volume that seems to have no overall curvature when we look at it from a cosmic perspective. Think of it like this: if you were an ant crawling on a very large, perfectly flat football field, you might assume you were on an infinite two-dimensional plane, even though that field has boundaries. We as observers are limited in our view, so we can only perceive the universe as flat from our perspective, stretching endlessly in all directions. This idea of a flat universe is a consequence of its overall density and expansion rate. The universe's density, a measurement of all the matter and energy within it, is in a delicate balance. If it were too dense, gravity would eventually win, pulling everything back into itself in a big crunch. If it were too sparse, the universe would expand forever, leading to a cold, empty state. Our universe seems to exist at a critical density, right at the tipping point between these two fates. This exquisite balance leads to the conclusion that the universe is largely flat, with only localized curves influenced by the immense gravitational presence of galaxies and the mysterious dark matter. It's as if a vast flat sheet has been gently dented in millions of places by the weight of massive objects, but the overall shape remains smooth and level. Now let's drift towards the idea of the edge itself. The concept of an edge can be misleading. because it suggests a physical boundary, a wall or a fence that marks the end of everything. But in our cosmic context, the edge of the observable universe is simply a time-limited horizon. We define it based on the distance that light has traveled since the beginning of the cosmos approximately 13.8 billion years ago. Our universe, in a way, is a story that has been unfolding for this long, and the light from the most distant chapters has only just reached us. Anything beyond that limit is still telling its story, and we just haven't received the first word yet. The true edge is not a wall, but a sphere of perception with us at the center. Every direction we look, we are seeing the oldest, most distant light. And because the universe itself has been expanding this entire time, that light has traveled a much greater distance than the 13.8 billion years its age would suggest. The radius of this sphere, our horizon, is about 46 billion light years. This number again defies easy comprehension, but it speaks to a profound truth. The fabric of space itself has stretched and expanded, carrying distant objects and the light they emitted far away from us, making our view both immense and yet still incomplete. This is a beautiful and somewhat melancholic thought. There are parts of the universe beyond that edge that we will never be able to observe, no matter how long we wait. Because of the ongoing expansion of space, some regions are moving away from us faster than light can travel. This isn't a violation of the laws of physics, but a property of the expanding medium of space itself. Imagine trying to run across a moving walkway. If the walkway is moving faster than you can run, you will never reach the end, no matter how hard you try. In the same way, the light from these distant regions is carried away from us faster than it can close the distance. Our understanding is therefore based on what we can see, but a gentle reminder lingers in the background that much, much more remains hidden from our view. This understanding of the edge invites us to be both humbled and inspired. The regions beyond our observable limit might contain galaxies, clusters, and phenomena similar to what we can see. But without direct observation, these areas remain speculative, like the whispered stories of a land we have never visited. The scientific inquiry into these unknowns is not a pursuit of absolute certainty, but a beautiful and ongoing exploration into the unknown frontiers of existence. It is a testament to our curiosity, a deep-seated human need to understand not just where we are, but what else might be out there. Now let's turn our attention to the oldest light we can see, a gentle glow that permeates the entire sky. This is the cosmic microwave background, CMB radiation, a relic from the universe's earliest moments. Imagine the universe as a newborn. At first, it was an incredibly hot, dense, and energetic place, so hot that light couldn't travel freely. It was a thick, opaque fog of plasma. But after about 380,000 years, the universe had expanded and cooled down enough for protons and electrons to combine, forming the first neutral hydrogen atoms. When this happened, the cosmic fog cleared, and for the first time, light was free to travel. This release of light, this first breath of the universe, is what we now detect as the CMB. It's the afterglow of the Big Bang, a faint cosmic hum that fills all of space. Over the billions of years since this ancient light has stretched and cooled as the universe has expanded. What was once a brilliant flash of light has now shifted into the microwave range of the electromagnetic spectrum, and today it is detected uniformly across the sky as a backdrop of nearly uniform energy and temperature, a mere 2.7 degrees above absolute zero. Detailed measurements of this background radiation have provided us with some of our most crucial insights into the early universe. Like an ancient faded map, the CMB reveals tiny fluctuations in temperature and density, the subtle irregularities that existed in the newborn cosmos. These subtle variations are not just random noise. They represent the seeds of structure formation. They were the tiny gravitational ripples that would eventually grow into galaxies, stars, and the vast cosmic web we see today. The fact that we can still detect these original seeds in the universe's oldest light is a testament to the elegant interconnected nature of cosmic history. The CMB also plays a key role in defining the limits of our observable universe. Since it comes from a time when the universe was just beginning to take form, it marks the farthest distance from which we can receive information. The CMB is our ultimate cosmic horizon, the very edge of our sphere of perception. It's a sort of cosmic map illuminating the conditions that prevailed shortly after the Big Bang and providing us with a storybook of the universe's evolution over time. By studying the small variations in temperature and density of this ancient radiation, researchers can make precise measurements of the universe's age, its composition, and its expansion rate. These insights help us to refine our understanding of the observable universe's boundaries and the vast structure extending beyond what we can see. We are not just looking at a static picture. We are seeing the distant past, the echo of creation itself. The exploration of these boundaries, both the theoretical and the observable, has transformed dramatically over the past century. At the beginning of the 20th century, we believed our galaxy was the entire universe, but then came the groundbreaking insights of astronomer Edwin Hubble, who, like a keen detective, studied the light from distant galaxies. He observed that these galaxies were moving away from us, and the farther they were, the faster they were receding. This was the first hint that our universe was not static, but was in fact expanding. This revelation fundamentally changed our perception of the cosmos, suggesting that the universe had a singular beginning, which we now call the Big Bang Theory. It was as if we had suddenly realized that the quiet, still painting we had been admiring was actually the slow-motion frame of a great unfolding drama. As our technology advanced, so did our methods of observation. The development of radio telescopes, satellites, and space observatories allowed scientists to peer deeper into space than ever before. The detection of the cosmic microwave background radiation in the mid-20th century provided the strongest evidence for the Big Bang Theory and offered us a glimpse into the very first moments of our universe. These findings led to better estimates of the universe's age and the mysterious contents that fill it, such as normal matter, dark matter, and dark energy. In recent decades, cosmologists have further refined our understanding of the universe's boundaries with sophisticated models and computer simulations. These models incorporate the latest observations from numerous telescopes, including the Hubble Space Telescope, which has contributed significantly to our knowledge of the universe's expansion rate and the distribution of galaxies within it. Newer satellite missions, such as the Planck mission, have provided detailed measurements of the cosmic microwave background, allowing for more exact calculations of parameters, like the density of ordinary matter and the influence of dark energy. Today, our understanding emphasizes that while the observable universe has a defined limit, the universe itself may be vastly larger or even infinite. The journey of discovery is ongoing, and each piece of new information reshapes our comprehension of the cosmos. It's a never-ending quest, a gentle and persistent pull toward the unknown, and we are just beginning to write the first chapters of this grand story. Let's now gently drift into the idea of cosmic expansion, a concept so fundamental to modern cosmology, it completely redefines our sense of place. It's a phenomenon whereby the universe is continuously growing, with galaxies moving away from each other over time. This isn't just an idea. It's a conclusion we've drawn from the careful observation of light. Back in the early 20th century, the astronomer Edwin Hubble, whose name we just heard, made a stunning discovery. He found that the light from distant galaxies was redshifted, meaning its wavelength had been stretched like a note dropping in pitch. The farther a galaxy was, the more its light was redshifted, and the faster it appeared to be moving away from us. This wasn't a sign of galaxies hurtling through empty space, but a more profound truth. The space between the galaxies was stretching, carrying them farther apart. Imagine baking a loaf of raisin bread. The raisins aren't moving on their own. It's the dough itself that is expanding, carrying the raisins with it. From the perspective of any single raisin, all the other raisins seem to be moving away. The farther a raisin is, the faster it seems to recede. That, in essence, is our universe. The galaxies are the raisins, and the dough is the very fabric of space and time. This expansion is a direct result of the Big Bang, which we now understand not as an explosion in space, but as the expansion of space itself from an incredibly hot, dense state. Initially, all matter and energy were concentrated in a single point, a state beyond our current understanding. As the universe began to expand, it cooled, leading to the formation of the first atoms, stars, and galaxies we see today. Understanding this expansion has been crucial for more than just defining the structure of our universe. It has also allowed us to estimate its age and predict its future. The rate of expansion is measured by a value known as the Hubble constant, which quantifies how quickly galaxies are receding from each other relative to their distance from us. This constant is a number that scientists have been refining for decades, and its value is a gentle ticking clock telling us how quickly the cosmic dough is rising. Cosmic expansion also profoundly influences our understanding of the universe's boundaries. It creates a natural limit to our observable universe, a kind of cosmic horizon. While we can observe a limited portion of the universe based on the light that has reached us since the Big Bang, the expanding space also means that there are regions we will never be able to observe. Imagine 2 points on that raisin bread. If the dough is expanding so fast that the space between them grows faster than the light can travel, they will never be able to see each other. Some galaxies are receding from us at speeds faster than light due to this expansion, making it impossible for their light to arrive here, even over an infinite amount of time. This is not a barrier of physics, but a property of the expanding canvas of reality. Furthermore, this expansion has deep implications for the universe's ultimate fate. Depending on the amount of matter and energy, particularly the elusive dark energy, the universe could continue to expand forever, eventually leading to a cold, dark era where galaxies drift so far apart they can no longer see each other. Or in other less favored scenarios, the expansion might one day slow and reverse, leading to a fiery, big crunch. So understanding this gentle stretch of the universe is essential not just for our current observations, but also for our quiet contemplation of the cosmos's distant future. Now let's explore the engine behind this expansion, a theoretical framework known as cosmic inflation. Imagine for a moment the universe as an old wrinkled sheet of fabric just moments after the Big Bang. Standard Big Bang theory struggled to explain why this sheet looks so smooth and flat on a large scale today. Why isn't the universe a lumpy, uneven mess? And how could regions of the universe that are now so far apart that light hasn't had time to travel between them be at the exact same temperature? This was called the horizon problem, and it was a deep puzzle. Cosmic inflation is a theoretical framework that proposes a dramatic solution. It suggests a super brief, hyperfast expansion of the universe that occurred just fractions of a second after the Big Bang, a period lasting from approximately 10 to 34 seconds to 10 to 32 seconds. During this fleeting explosive moment, the universe grew exponentially in size from subatomic scales to nearly the size of a galaxy. This rapid growth, like a swift pull on that wrinkled sheet, would have smoothed out any initial irregularities, making the universe appear remarkably uniform and flat on a large scale. It was a cosmic straightening iron, erasing the wrinkles of creation. This theory also beautifully addresses the flatness problem, explaining why the universe's geometry is so close to flat. Inflation stretched the universe so immensely that any initial curvature would have been flattened out, much like how the surface of a large beach ball looks completely flat from the perspective of a tiny ant. In addition to smoothing out the universe, inflation also provides a beautiful mechanism for the formation of the large-scale structures we observe today. During that brief hyperfast expansion, tiny microscopic quantum fluctuations that were present in the vacuum were stretched to cosmic scales. These quantum ripples in the fabric of the universe, once infinitesimal, became the seeds of structure formation. They were the subtle variations in density that would later grow through the gentle pull of gravity into the clusters of galaxies and the vast cosmic web we see today. These fossilized quantum fluctuations have been detected in the cosmic microwave background radiation, providing powerful indirect evidence for the inflationary theory. Cosmic inflation has significant implications for our understanding of the early universe. It helps explain the initial conditions that were necessary for the Big Bang to unfold as it did, and it suggests that our observable universe might just be a small part of a much, much larger cosmic landscape. It opens up profound questions about what may exist beyond our observable universe and invites us to explore the fundamental nature of existence itself. As research continues in this area, inflation remains a powerful tool for understanding the origins and evolution of our universe, a gentle whisper from a time we can barely fathom. It's a story of how something incredibly complex and beautiful could arise from a moment of incredible simplicity and power. Let's now turn our attention to the mysterious force that is currently dominating the narrative of our cosmos' dark energy. This force, a mysterious and unseen entity, is believed to be responsible for the accelerated expansion of the universe. For a long time, scientists thought that the universe's expansion should be slowing down due to gravity, the great cosmic anchor pulling everything together. But in the late 20th century, observations of distant supernovae, a type of exploding star, revealed something completely unexpected. These supernovae, which act as cosmic standard candles because of their consistent brightness, appeared dimmer than they should have been. This could only mean one thing: they were farther away than our models predicted, which suggested that the universe's expansion was not slowing down, but was in fact speeding up. It was a discovery that shocked the scientific community, as if the gentle forward motion of a ship had suddenly begun to accelerate with no sail in sight. Dark energy is the term we give to this mysterious force. We believe it makes up approximately 70% of the total energy content of the universe, but we don't know what it is. One leading hypothesis is that it is a cosmological constant, a form of energy inherent to the fabric of space itself. In this view, as space expands, more space is created, and with it, more dark energy, exerting a constant, repulsive gravitational force that pushes the cosmos apart. It's like a soft, invisible pressure that fills every corner of existence, and as the container of the universe gets bigger, the pressure increases, pushing the walls out even faster. The acceleration of the universe complicates our understanding of its ultimate fate. If dark energy continues to dominate, the universe may expand indefinitely, leading to a scenario known as the Big Freeze. In this outcome, galaxies would drift so far apart that we would eventually be alone in a vast, dark, and cold cosmos. Stars would burn out, and the universe would become a cold, dark landscape, a silent and still expanse. On the other hand, alternative theories suggest that dark energy could be more dynamic, a changing force that might one day weaken or strengthen, leading to different cosmic fates. For instance, if its repulsive force were to grow stronger over time, it could lead to the Big Rip theory, where the acceleration would intensify to the point of tearing apart galaxies, stars, planets, and eventually even atoms themselves. It is a chilling idea, a universe that ends not with a whimper, but with a tearing, a shredding of the very fabric of reality. Current research focuses on trying to understand the true nature of dark energy, including whether it is a fundamental property of space or a more dynamic, changing field. Observations from ongoing and future projects, including large galaxy surveys and improved measurements of the cosmic microwave background, aim to unravel these mysteries. By studying its effects, scientists hope to gain insights into the ultimate fate of the cosmos and refine our models of cosmic expansion. Dark energy is a gentle, steady force that reminds us that even when we think we have a handle on the universe, there are still vast, unseen powers at play, guiding its grand journey towards an unknown end. Now let's turn our attention to the great mystery of dark matter, a ghostly substance that binds the universe together. If dark energy is the invisible hand that pushes the cosmos apart, then dark matter is the unseen scaffold that holds everything in place. We have known for a long time that something is missing from our cosmic accounting. Galaxies, like giant spinning pinwheels, rotate so fast that the stars on their outer edges should have been flung off into space, much like a child flying off a fast spinning carousel. But they don't. They stay together in a tight gravitational embrace. The only way for this to happen is if there is far more mass in the galaxies than we can see. This extra mass, which doesn't seem to emit, absorb, or reflect light, is what we call dark matter. We don't know what it is, and we have never directly observed it, but we can feel its presence through its gravitational pull. We believe that dark matter makes up about 27% of the total mass energy content of the universe. Compare that to the mere 5% of ordinary or baryonic matter, the stuff we are made of, the stars, planets, and galaxies we can see. This means that for every star, planet, or gas cloud, you see there is more than 5 times as much dark matter, silently holding the cosmos together. Imagine a vast, intricate, and transparent fishing net that has been cast across the universe. The galaxies and their clusters are the glistening jewels caught in the threads of this net, but the net itself, the dark matter, is completely invisible. This invisible framework of dark matter is crucial for the formation of the large-scale structures we observe. Without it, the matter we can see would not have been able to clump together to form galaxies and clusters in the time since the Big Bang. Dark matter provided the gravitational wells, the cosmic foundations for all the luminous structures to form. The mysterious nature of dark matter also opens up fascinating possibilities about what might exist beyond our observable universe. If dark matter is an unknown particle, it might interact with the fabric of space-time in ways we don't yet understand. Some theories propose that dark matter could be a bridge between our universe and others, a kind of unseen medium that connects different realms. For instance, if there are multiple universes with varying physical laws or dimensions, dark matter could have different manifestations or properties in those realities. Such interactions could create gravitational influences that leave detectable traces within our universe, even if the other universes remain completely inaccessible to us. The study of dark matter is therefore not just about filling in a blank spot in our cosmic inventory. It is a profound inquiry into the fundamental nature of reality itself. Its existence challenges our assumptions about what constitutes matter and energy, and it forces us to consider a cosmos that is far more complex and intricate than our limited senses can perceive. As scientists continue their quest to directly detect dark matter particles, perhaps through experiments deep underground or in particle accelerators, every new piece of information we gather about this ghostly substance will also be a small step closer to understanding the great unseen tapestry of the cosmos and the potential for a reality that extends far beyond our current sight. This brings us to a captivating but highly speculative idea: the existence of primordial black holes. These are not the black holes that form from the collapse of massive stars. Instead, primordial black holes are thought to have formed in the first moments after the Big Bang, when the universe was an incredibly hot and dense sea of matter and energy. At that time, tiny density fluctuations in this primordial soup could have in certain circumstances collapsed under their own gravity to form black holes. These are the black holes of cosmic infancy, and they offer a unique window into the universe's earliest conditions. Unlike stellar black holes, primordial black holes could come in a wide range of sizes. They could be incredibly small with masses less than that of an asteroid, or they could be much larger. The existence of these smaller primordial black holes is particularly intriguing because it raises a very elegant possibility. Could they be the mysterious dark matter we have been searching for? Some theories propose that if such black holes exist in sufficient quantity, they could account for a significant portion, or even all of the elusive dark matter that makes up the universe's mass. This is a very compelling thought, as it would solve a major cosmic puzzle by using a known type of object, albeit one that formed in a very different way. Furthermore, the formation and characteristics of primordial black holes could provide a hint about other realities or different regions of the universe. If certain mass ranges were associated with multiple formation processes or different physical conditions, it might hint at a multiverse concept where our universe is just one of many each, with distinct physical principles. Perhaps the conditions that gave rise to one type of primordial black hole in our universe were just one of many possible outcomes in a larger cosmic landscape. The study of these enigmatic objects intersects with the exploration of cosmic inflation, the period of rapid expansion that smoothed out the early universe. Understanding how density fluctuations led to the genesis of these black holes may inform our broader theories on inflation and the formation of large-scale structures, giving us a deeper look into the conditions of creation itself. As scientists continue to probe the nature of primordial black holes, they are not only enriching our knowledge of the early universe, but also pushing the boundaries of our understanding of the cosmos and the potential for a reality that extends far beyond our current view. Now let's allow our minds to float towards the idea of the cyclic model of the universe, an alternative to the traditional Big Bang theory. In this framework, the cosmos is not a story with a single beginning and a single end, but rather an infinite, rhythmic cycle of expansions and contractions, like a great cosmic heartbeat. Instead of originating from a singular explosive event, this model suggests that our universe continuously evolves through these cycles. Each cycle begins with a Big Bang, leading to a period of expansion, and eventually culminates in a contraction phase, where the universe collapses back in on itself in a Big Crunch. It then rebounds from this state of extreme density in another Big Bang, restarting the cycle all over again. This model challenges our traditional linear view of time and existence. It suggests that before our current universe, there was a preceding universe that contracted, and before that, another one stretching back in a timeless, eternal rhythm. The universe in this view has always been, in one form or another, a story without a true beginning or end. One of the driving concepts behind this cyclic model is the delicate interplay between gravity, dark energy, and other cosmic forces. As the universe expands, dark energy dominates, pushing everything apart. But the theory proposes that this acceleration may be temporary. Over a vast amount of time, gravitational forces could eventually dominate again, initiating a contraction phase. This cycle would repeat indefinitely, a continuous process of cosmic rebirth. The cyclic model is not just a poetic idea. It is a serious alternative that seeks to address some of the puzzles of the conventional Big Bang model, particularly those related to the initial conditions. It suggests a way for the universe to be born without the need for a sudden, abrupt inflationary period, which some find to be a delicate and fine-tuned condition. Instead, the universe's properties, such as its flatness and uniformity, could be a natural consequence of having gone through countless cycles of expansion and contraction. In this beautiful eternal view, the universe is not a singular event, but a continuous process of cosmic transformations. It invites us to consider time not as a one-way street, but as a great looping river flowing through an infinite landscape of creation and destruction. The cyclic model offers a profoundly different perspective on the nature of cosmic events and the ultimate fate of the universe, and it is a powerful reminder that our current understanding of reality may only be one chapter in a much, much longer story. As we lie here in the quiet darkness, it is a comforting thought that the universe may be a timeless entity, forever breathing, forever reborn. The ekpyrotic scenario is another fascinating alternative that complements our discussion of the cyclic model. It presents a different view of cosmic creation, one that moves away from the singularity of the Big Bang and instead points to the grand ballet of higher dimensions. This model, which arises from the principles of string theory, proposes that our universe emerged not from an explosion from a single point, but from the collision of two vast multidimensional objects known as brains. Imagine our universe as a three-dimensional brain, floating in a higher dimensional space called the bulk. In this vast extra-dimensional space, there may be other brains, perhaps even a neighboring one invisible to us. The ekpyrotic scenario suggests that our universe came into being when two of these brains collided. This collision, like the gentle clapping of two immense sheets of paper, would have generated a tremendous amount of energy, which then manifested as the matter and energy we see today. This cosmic clap would have set off an expansion, a universe-wide stretch that we now observe as the Big Bang. This model neatly addresses some of the same puzzles as inflation, such as the flatness problem, without needing a rapid hyperfast expansion. The homogeneity, anisotropy of our universe could be a natural consequence of the slow, gentle movement of the brains towards each other and their eventual collision. It also provides a compelling framework for a cyclical universe. After the collision and subsequent expansion, the brains would eventually move apart and then, over an incredibly long period, be pulled back together by some unseen force for another collision, giving rise to another universe. This is a universe that is perpetually being born, dying, and being reborn in a timeless cosmic dance of brains. The ekpyrotic model offers a new way to think about the origins of our universe, one that integrates the ideas of higher dimensions and string theory into a cohesive narrative. It suggests that our universe is not an isolated event, but a part of a larger, grander story unfolding in a multidimensional cosmos. The thought that the very existence of our reality could be the result of a gentle, silent collision between two immense invisible sheets of reality is a beautiful and humbling idea. It reminds us that there may be layers upon layers of existence, a nested set of realities that we are only just beginning to imagine. And as we close our eyes, we can picture this great quiet dance of the brains forever giving birth to new worlds, new stars, and new possibilities. Now let's allow our minds to take a great sweeping leap into the realm of the multiverse, an idea so vast and profound, it makes the single universe model feel small and quaint. The multiverse at its core is the suggestion that our universe may be just one of many distinct universes existing simultaneously. It's a concept that stems from several different theoretical frameworks in cosmology and physics, each one painting a slightly different picture of what these other universes might be like. They could be like bubbles in a great cosmic sea, or pages in an immense library of every possible story. The multiverse concept challenges our traditional view of a single isolated universe, expanding our notions of reality and existence far beyond our wildest imaginings. One of the most prominent theories that gives rise to the idea of a multiverse is, perhaps surprisingly, a concept we've already touched on: cosmic inflation. We previously imagined inflation as a brief hyperfast expansion that smoothed out our universe, but in a more complex view, this inflationary process may not have stopped everywhere at once. It may be eternal. Imagine the inflating cosmos as a vast, frothy ocean. In certain regions, the inflation stopped, the foam settled, and a bubble universe, like our own, was born. But in other regions of this ocean, the inflation continued, creating a new, ever-expanding sea from which other bubbles could form. This ongoing process of inflation, perpetually creating new pocket universes, is known as eternal inflation. In this scenario, our universe is just one of many bubbles born from the same inflating field, but now completely separate. Each bubble can have its own unique physical laws, constants, and dimensions of space and time. This opens up an astonishing possibility. The constants of nature in our universe, which seem so perfectly fine-tuned for life, might simply be one of countless variations. In a universe next to ours, gravity might be stronger, light might travel at a different speed, or there might be no stars at all. The very rules that govern reality could be different from one bubble to the next, creating an expansive tapestry of realities that exist alongside our own, a vast cosmic garden with an infinite number of unique flowers. This idea of a multiverse isn't limited to the macro scale of cosmology. It also finds a strange and beautiful echo in the microscopic world of quantum mechanics. The many worlds interpretation, a mind-bending idea that emerged from the work of physicist Hugh Everett III, suggests that all possible outcomes of a quantum event actually take place in separate branching universes. In traditional quantum mechanics, a particle exists in a kind of blurred state of possibilities until we measure it, at which point its wave function collapses into a single, definite outcome. The many worlds interpretation, however, proposes something different. There is no collapse. Instead, every time a quantum event with multiple possible outcomes occurs, the universe splits. Imagine a single stream flowing forward and it comes to a rock. The stream doesn't just choose to go left or right. It splits into two, with one stream flowing left and the other flowing right. In the same way, when a particle can spin either up or down, the universe doesn't just choose one outcome. It splits into two parallel non-communicating realities. In one, the particle spins up. In the other, it spins down. This branching process continues for all quantum events, creating an infinitely complex, ever-expanding web of parallel realities. Every choice we make, every quantum decision, leads to the creation of a new universe, generating an expansive tapestry of realities that exist parallel to one another. The implications of this are profound and a little dizzying. It suggests that every possible version of our lives, every alternative path we could have taken, is unfolding right now in another reality. The multiverse idea also finds a compelling home in string theory, particularly through a framework known as the landscape multiverse. String theory suggests that the fundamental building blocks of the cosmos are not point-like particles, but rather tiny vibrating strings. These strings exist in multiple dimensions, typically 10 or 11, far more than the 4 we are familiar with. The way these extra dimensions are curled up and compacted can vary, and each different configuration can lead to a distinct universe with its own set of physical laws, constants, and forces. Imagine a vast, multi-dimensional landscape. Each valley or hill in this landscape represents a different configuration of these extra dimensions and thus a different possible universe. There may be a colossal number of these valleys and almost infinite number of ways for the universe to be. Our universe, with its specific laws of physics and constants, is just one of these valleys. The existence of this vast landscape of possibilities offers a beautiful explanation for why our universe has the specific properties it does. Perhaps in a cosmic sense, our universe just happens to be in a valley that is stable and conducive to the formation of stars, galaxies, and life. This concept not only challenges our preconceived notions of existence, but also opens doors to exploring how universes might interact or be entirely isolated from each other, forever changing our perspective on reality itself. Another intriguing concept is the ultimate multiverse, a more abstract idea that stems from the notion that if mathematical structures exist independently of our universe, then any conceivable universe governed by consistent mathematical laws could also exist. This is the most profound and all-encompassing idea of the multiverse, where every possible configuration that adheres to logical principles would manifest as a unique universe. In this view, our universe is not just one of many, but one of every mathematically possible universe, a truly infinite collection of realities that are all equally real. The implications of the multiverse concept are, to say the least, profound. It raises fundamental questions about the nature of existence, reality, and our place within it. If other universes exist with different laws of physics, it brings into question the uniqueness of our universe and suggests that the constants we observe may merely be one set of possibilities among a sea of variations. This challenges our understanding of cosmology and physics, as well as our philosophical perspectives regarding existence and life. While the multiverse remains a tantalizing hypothesis, it presents significant challenges in terms of empirical verification. We cannot, with our current tools, peer into another universe. There is no direct evidence for their existence, leading to ongoing debates within the scientific community about the multiverse's legitimacy as a scientific theory. However, the lack of direct evidence doesn't diminish the beauty and power of the idea. It is a space for our imagination to roam, a place where we can quietly contemplate the possibility of other worlds, other lives, and other realities, all existing just beyond the edge of our perception. It is a concept that sparks curiosity and inspires new lines of inquiry, a gentle reminder that the universe in all its forms is likely far stranger and more beautiful than we can possibly imagine. As we fall into a quiet sleep, we can take comfort in the possibility that our universe is a part of something much, much bigger, a vast interconnected tapestry of existence that stretches beyond our single isolated reality. We are not alone in a sense, but part of a grand and beautiful community of cosmic stories. Let's now gently pivot our gaze to the theoretical objects that might bridge these vast realities, the fascinating, almost mythical structures that physicists have only dreamed about. We'll begin with cosmic strings, which are not strings in the guitar sense, but rather one-dimensional thread-like defects in the fabric of space-time. They are a prediction of certain models in theoretical physics, particularly those related to string theory and cosmology. If they exist, cosmic strings would be extraordinarily thin, yet incredibly dense, with an immense gravitational pull, a kind of gravitational ghost in the cosmic machine. The formation of cosmic strings is thought to have happened in the universe's earliest moments, right after the Big Bang. As the universe underwent rapid expansion and cooling, it experienced various phase transitions, similar to how water freezes into ice. During these cosmic phase changes, the fields that govern the fundamental forces of nature could have settled into different states, and in the process, imperfections could have arisen in the fabric of space-time. These imperfections, these tiny wrinkles in the cosmic fabric, are what we call cosmic strings. They would have formed a network stretching across vast distances, potentially spanning entire regions of the universe, and once established, they would possess incredibly strong gravitational fields. This is where the story gets truly interesting. Cosmic strings, if they exist, could have significantly influenced the structure of the universe as it evolved. Their immense gravitational pull would have acted like a gravitational scaffolding, a kind of cosmic skeleton around which matter could cluster. This would have led to the development of galaxies and other cosmic structures as matter accumulated along the strings. In this way, cosmic strings could provide a beautiful and elegant mechanism for explaining the lumpy, uneven distribution of matter we observe in the universe today. They were the original cosmic magnets, pulling the primordial soup of gas and dust together to form the first galaxies. The strings would have provided the necessary gravitational seeds, allowing cosmic structures to form more efficiently than gravity alone would accomplish. The most captivating aspect of cosmic strings, however, is their potential to influence our understanding of what lies beyond our observable universe. Because these strings might extend beyond the limits of what we can see, they could serve as connections to regions of the universe that remain hidden from our direct observation. If they are massive and long enough, their gravitational fields would warp space-time around them, creating a powerful effect known as gravitational lensing. This bending of light could make it possible for us to observe phenomena that originate from portions of the universe we cannot directly access, a kind of cosmic periscope peeking into the great unknown. Additionally, cosmic strings could provide a framework for exploring concepts such as multiple dimensions or higher dimensional spaces. They might help us understand how various realms of the universe could interact or be connected, strengthening the case for theories like the multiverse. By examining these strings, we could probe questions about the structure and evolution of the cosmos on scales even larger than our observable limits. If cosmic strings exist, understanding their properties might help unlock the mysteries of the universe and guide us toward comprehending the broader realities that extend well beyond the boundaries of our perception. Now let's explore a two-dimensional counterpart to these one-dimensional strings, domain walls. These are fascinating topological defects that are theorized to have emerged in the early universe not as threads, but as vast, two-dimensional surfaces. They are a bit like the boundaries that form between different regions of ice and water as water freezes. As the universe cooled after the Big Bang, it underwent a series of phase transitions. In certain models, if a field that governed a fundamental force settled into a specific value that wasn't uniform across the cosmos, different regions with different vacuum states could have developed. The boundaries between these regions are the domain wall's immense two-dimensional planes that separate different cosmic phases. The formation of domain walls is associated with a process called symmetry breaking. This is a beautiful concept where, in the high-energy state of the early universe, certain physical laws were united or symmetric. As the universe cooled, this symmetry was broken, and the forces of nature separated. If this symmetry was broken in different ways in different places, domain walls would have formed at the boundaries of these regions. The boundary created by the domain wall would have distinct physical properties compared to the regions on either side, often exhibiting unique energy densities and behaviors. This separation might have impacted the evolution of the universe by influencing how matter moves and interacts across these different phases. Domain walls, much like cosmic strings, could have exerted strong gravitational effects on the surrounding matter fields. They might have acted as cosmic barriers, influencing where matter accumulated and leading to large-scale non-uniformities in the cosmos. However, if domain walls exist, their gravitational effect would be so immense that they would have long ago crushed the universe into a pancake, a fate we have clearly avoided. This suggests that if they exist, they must have some very special properties, or they must have been destroyed in the early universe, or perhaps they exist only in a more subtle form. But their theoretical possibility is still a powerful tool for thought. If they could separate different regions of space, they might lead to fascinating scenarios regarding the conditions and properties of those regions. Imagine one side of a domain wall being governed by one set of physical laws, while the other side exhibits entirely different characteristics. This relationship opens up exciting avenues for exploring the multiverse, where different regions of space could follow distinct physical rules. These possibilities challenge our understanding of the universe and encourage deeper inquiries into the fundamental nature of reality and how various phases of existence can coexist and influence one another throughout cosmic history. The concepts of cosmic strings and domain walls, while distinct, both represent intriguing possibilities for how our universe might connect with other universes. Each of these structures could act as boundaries or gateways, facilitating interactions between different regions of spacetime, or potentially different universes altogether. Cosmic strings as one-dimensional defects could theoretically act as cosmic highways, a kind of inter-universal transport system. Some hypotheses suggest that they could connect to other topological defects or even wormholes, potentially allowing for a form of travel between different regions of space or even different universes. This connectivity could enable a kind of transportation across vast distances, making seemingly distant regions accessible, at least in theory. Domain walls, on the other hand, as two-dimensional boundaries separating different physical phases, may also function as gateways. They could establish sharp boundaries between regions that obey different physical laws or fundamental constants. If such domains exist, transitioning across a domain wall might expose an observer to an entirely different physical reality. This provides a framework where two separate regions of space could experience varying realities, leading to the idea that domain walls might delineate distinct universes within a larger multiverse context. Both cosmic strings and domain walls, though primarily theoretical, prompt powerful questions about the nature of existence and our understanding of the cosmos. If we consider their roles as potential gateways, we must explore how their interactions might influence the properties of the universe as a whole. How would the presence of a cosmic string impact the gravitational dynamics around it? How might a domain wall dictate the kinds of interactions that occur on either side? These inquiries encourage a deeper engagement with the mysteries of the universe and highlight the interconnectedness of different regions or realities. Both structures challenge our perceptions of space and universality, engaging us in discussions about the roles they might play in connecting different parts of the cosmos and expanding our understanding of the nature of reality. They are not just abstract concepts, but potential keys to unlocking the insights behind the multiverse and the fundamental workings of our universe. They are whispers from the cosmos, hints of a reality that is far more complex and beautiful than we can currently imagine. To confirm the existence of these incredible ephemeral structures, scientists would have to search for their subtle signatures. For cosmic strings, one of the most significant observational clues would be the formation of a specific type of gravitational lensing known as a cosmic string lens. The string's immense gravity would be so strong that it would bend the light from distant objects, creating unique visual distortions. This could result in the formation of rings or arcs around a string. We could potentially identify these effects by analyzing the light from background galaxies and seeking out patterns that cannot be explained by conventional lensing, caused by a massive galaxy or cluster. Cosmic strings could also leave imprints in the cosmic microwave background, CMB radiation, creating slight temperature fluctuations that would manifest as non-Gaussian features, differing from the smooth isotropic predictions of our standard cosmological model. Domain walls, on the other hand, would be characterized by different signatures. If they exist, they would likely influence the density fluctuations in the universe, creating regions of high energy density that would affect galaxy formation and the large-scale distribution of matter. We might look for patterns in the large-scale structure of the universe, such as unexpected voids or anisotropies that correspond to the locations of these domain walls. They too might generate effects in the CMB, causing sudden temperature changes across the background radiation, a kind of cosmic seam in the fabric of existence. While no conclusive evidence for cosmic strings or domain walls has yet emerged, these avenues of research show us that we are on the cusp of expanding our understanding of the universe's structure. Future advancements in observational techniques, refined computational models, and more extensive data sets may one day lead to critical discoveries that help clarify whether these fascinating theoretical objects are a real part of our universe. Until then, they remain a beautiful testament to the power of human imagination and our relentless drive to understand the cosmos even when the answers are not yet within our grasp. Now let's turn our quiet minds to a truly mind-bending idea, one that asks us to reconsider the very nature of reality itself. This is the holographic principle, a thought-provoking concept that suggests our three-dimensional universe might be a grand illusion, a projection from a lower dimensional surface. It's like imagining our entire reality with all its galaxies, stars, and even ourselves as a hologram, much like the three-dimensional image on a credit card that is encoded on a two-dimensional surface. The principle emerged from the study of black holes, those cosmic behemoths that swallow everything, even light. The key insight came from physicists who noticed that a black hole's maximum amount of information, a measure of its entropy, was not related to its volume as one might expect. Instead, it was directly proportional to the area of its event horizon, the two-dimensional surface that marks the point of no return. This simple but profound relationship hinted at something incredible. Perhaps all the information contained within a volume of space could be encoded on the two-dimensional surface that surrounds it. This implies that everything we experience in 3 dimensions, all the depth, all the space, all the matter, could be viewed as arising from information that is somehow hidden on a flat two-dimensional boundary. It is a concept that fundamentally alters our grasp of dimensions and reality. By reframing our understanding of the universe through the lens of the holographic principle, new perspectives on gravity and quantum mechanics emerge. For a long time, these two foundational pillars of physics have struggled to coexist within a single framework. Gravity, as described by Einstein's theory of general relativity, is a smooth, continuous curvature of space-time. Quantum mechanics, on the other hand, describes a microscopic world that is lumpy, discrete, and probabilistic. The holographic principle offers a potential bridge between these two worlds. It suggests that perhaps gravity itself is not a fundamental force, but an emergent property, a kind of collective effect that arises from the underlying quantum-level information encoded on that two-dimensional surface. It's a bit like how the smooth, continuous flow of a river is an emergent property of billions of tiny individual water molecules. In this view, the universe we see is not the fundamental reality, but a manifestation of a deeper, more profound truth. The holographic principle also has profound implications for what exists beyond our observable universe. If our three-dimensional reality is a projection, it suggests that the universe might extend far beyond what we can currently see, with regions of space that are fundamentally linked through deeper, higher dimensional structures. Our observable universe might be just a fragment of a much larger interconnected cosmic tapestry that transcends our current observational capabilities. It's like being able to see only a small piece of a vast, complex movie screen, with the rest of the movie playing out silently. Just outside our view, all of it projected from a single, unseen source. Such a perspective also generates questions concerning the nature of causality and the flow of information in the universe. If the information that describes our universe can be encoded on boundaries, then changes or events in distant regions of the cosmos may still have implications for our observable universe, albeit indirectly through the unseen holographic connection. This leads us to another fascinating theoretical concept that challenges our understanding of space-time quantum foam wormholes. At the intersection of quantum mechanics and general relativity at the smallest possible scales, the universe is thought to be anything but calm. This idea suggests that at the Planck scale, a minuscule fraction of a meter spacetime is not smooth and continuous. Instead, it exhibits a frothy, fluctuating structure, a turbulent sea of virtual particles and fields that constantly pop in and out of existence. This chaotic, ever-changing medium is what we call quantum foam. Within this restless, churning sea of quantum foam, tiny connections or tunnels might spontaneously appear and disappear. These are the wormholes of quantum foam theoretical passages through space-time that could connect different points in our universe, or even different universes altogether. Rather than being stable, traversable bridges, these wormholes are thought to exist in a fluctuating, ephemeral state, appearing and vanishing in a flash. But during their fleeting existence, they could, in theory, facilitate a form of communication or interaction between universes, allowing for the exchange of information particles or energy across the boundaries of different realities. Such interactions would not be observable in the traditional sense, emphasizing the fundamentally probabilistic nature of the quantum world. The chaotic nature of quantum foam suggests that while these connections are fleeting, they could still have significant effects on the dynamics of the involved universes. They are a constant, restless hum in the fabric of reality, a perpetual churning that might be the source of new realities. The implications of quantum foam wormholes extend into the realm of information theory and the study of holographic principles. If information is fundamentally linked to the structure of spacetime as the holographic principle suggests, then these tiny connections could hold the keys to understanding how information and energy are transferred across cosmic scales. Researchers have theorized that exploring these connections might even help illuminate the behaviors of dark matter and dark energy, which remain enigmatic components of our universe. The existence of these wormholes would also suggest that the behavior of particles is not entirely limited to our familiar three-dimensional space, but could entail complex interactions with higher dimensional structures or neighboring universes. This is a universe that is not static and isolated, but one that is constantly in flux, connected to a vast, unseen network of possibilities. The idea of quantum foam wormholes connecting our universe to others at the smallest scales presents an exciting frontier in theoretical physics. As researchers delve deeper into quantum mechanics, general relativity, and the nature of spacetime, The exploration of these wormholes may reveal profound insights into the interconnectedness of existence, helping to unlock the mysteries of reality and the potential for interactions among diverse realms. This brings us to a concept that takes the idea of a self-creating universe to its ultimate conclusion, the cosmic evolutionary algorithm. This fascinating model suggests that the fundamental constants of nature in our universe, which seem so perfectly fine-tuned for life, are not fixed or arbitrary. Instead, they emerged through a dynamic process akin to natural selection or optimization in biological evolution. In this framework, the cosmic evolutionary algorithm would act as a guiding mechanism, a cosmic parent that iteratively explores various configurations of these constants across a vast landscape of potential physical realities. Imagine a multiverse filled with countless universes, each with a different combination of physical constants: the strength of gravity, the speed of light, the mass of an electron. In this cosmic landscape, some universes would be born and immediately die, unable to form stable atoms or stars. Others would exist in a cold, dark state with no chance for life to ever emerge. But a few like our own would possess a delicate balance of forces and structures that allows for the formation of galaxies, stars, planets, and eventually life. The cosmic evolutionary algorithm would, in a sense, select these universes, favoring the configurations that promote stability, complexity, and the conditions for the development of life. This evolutionary filtering could enhance the likelihood of universes that possess the balance of forces and structures needed to allow for the emergence of life and consciousness. The implications of a cosmic evolutionary algorithm extend not only to the constants of nature, but also to the fundamental laws of physics. If these laws are adjustable or can fluctuate within this algorithmic framework, it suggests that our universe could be the product of an ongoing dynamic process rather than a fixed endpoint. It challenges our understanding of fine-tuning the apparent precision with which the constants of nature allow for life and complexity. If these constants are outcomes of a cosmic evolutionary process, it raises profound questions about the nature of life itself and its relationship with the cosmos. Life, in this view, becomes an essential factor in the evolutionary algorithm, potentially influencing how the constants are set or modified in neighboring universes. The idea of a cosmic evolutionary algorithm provides a compelling avenue for exploration in cosmology, physics, and philosophy. It invites a deeper reflection on the interconnectedness of existence, evolution, and the mysteries of the cosmos. It suggests that the universe is not just a stage upon which a story unfolds, but a living, breathing entity that is constantly evolving and optimizing itself, creating new possibilities and new realities with every cosmic breath. As we lie here in the quiet of our own universe, we can imagine ourselves as a part of a much larger, more intricate process, a living experiment in a grand cosmic lab with a purpose we are only just beginning to grasp. This brings us to another beautiful poetic idea: reality fractals. This concept proposes a framework in which the structure of the universe exhibits self-similar patterns across different scales, leading to the idea of infinite, nested universes. Fractals are mathematical constructs that display repeating patterns at various levels of magnification, such that smaller sections of the fractal resemble the whole. Applying this concept to cosmology suggests that the universe might not only have similarities in structure at large scales, such as galaxies clustering in filaments, but also duplicate configurations at smaller and smaller scales, potentially leading to the existence of universes nestled within larger cosmic structures. In this model, every universe could be viewed as a fractal with its own set of physical laws and properties, shaped by similar underlying principles. Large-scale structures like galaxy clusters could maintain features indicative of the same principles governing phenomena at smaller scales, like atomic structures or subatomic particles. This notion implies that as one zooms closer to any point in the universe, they might discover structures that replicate the larger cosmic framework. suggesting a uniformity of patterns dictated by the fundamental laws of physics. The concept of reality fractals might also furnish an explanation for the multiverse. If our universe is just one iteration of a fractal pattern, then there could be countless other universes that emerge from the same underlying principles but manifest distinct characteristics. Each nested universe would retain certain features of the larger fractal pattern while diverging in essential ways due to variations in initial conditions, physical constants, or dimensional constraints. This perspective challenges our perceptions of time and sequence within the cosmos. If the structure of reality operates on fractal principles, it could imply that different layers of existence experience time differently or even influence one another. The interconnectedness of these layers might allow for unique interactions that span universes, further enriching the complexity of reality. Ultimately, the idea of reality fractals creating infinite nested universes provides a compelling lens through which to explore the interconnectedness of structures across various scales. As scientists continue to investigate the nature of the cosmos, this concept could lead to innovative theories and models that encourage deeper inquiry into the fundamental principles governing existence. Such inquiries might reveal not only the nature of our universe, but also the nature of reality itself, reshaping our understanding of the cosmos as a whole, and reminding us that there is a deep, quiet, and elegant order to the great cosmic chaos we perceive. Let's now turn our gentle gaze towards some of the perplexing oddities and large-scale structures that stretch across our universe, the parts of the cosmic canvas that don't quite fit the picture we've drawn. These are the whispers from the great, beyond the subtle hints that our understanding may be incomplete. We begin with cosmic voids, the vast empty spaces in the universe that contain very few galaxies or matter compared to denser regions. These voids can stretch for hundreds of millions of light years, making up a significant portion of the universe's large-scale structure. In contrast to the bright filaments and clusters where galaxies congregate, these voids appear as great cosmic emptiness, highlighting the intricate web-like distribution of matter throughout the cosmos. The study of cosmic voids has revealed that they are not just vast absences of matter. They play a critical role in the evolution and behavior of the universe. Think of the universe as a giant three-dimensional sponge. The galaxies and clusters are concentrated along the threads of the sponge, while the voids are the empty spaces in between. The gravity from the denser filaments pulls galaxies toward them, while the voids gently push against them, creating boundaries that define the entire structure. By observing the properties and distributions of voids, astronomers gain insight into the overall dynamics of the universe and the processes that shaped it. The relationship between cosmic voids and regions beyond our observable universe is a subject of great intrigue. Since these voids represent some of the largest structures in the cosmos, they may suggest that similar empty regions exist beyond the limits of what we can currently observe. Our universe continues to expand, and the light from those distant regions may not yet have reached us, leaving the possibility of vast unseen areas filled with voids or different structures beyond our observational horizon. Furthermore, some cosmological models propose that these voids could be tied to the fundamental dynamics of the multiverse, where multiple universes exist in diverse configurations. If our universe is just one of many, the principles governing the creation and arrangement of matter may operate differently in other realities, leading to different patterns of voids and structures. By studying the nature of cosmic voids within our universe, researchers can glean clues about the potential character of regions beyond our observable limits, offering a tantalizing glimpse into the underlying fabric of reality itself. Adding to the mystery are supervoids, enormous regions of space that are even less dense than average, spanning hundreds of millions of light years and containing far fewer galaxies than a typical cosmic void. The existence of these vast underpopulated areas presents intriguing challenges to our understanding of cosmic structure formation. Current cosmological theories, particularly those related to the distribution of galaxies and dark matter, are based on the premise that matter is relatively uniformly distributed in the universe, leading to the predictable sponge-like structure. Supervoids, however, suggest that large regions of space can exist in relative emptiness, prompting scientists to reconsider how these vast voids formed without resulting in noticeable gravitational consequences on surrounding structures. The presence of supervoids also raises questions about the role of dark energy in cosmic evolution. Dark energy is believed to be responsible for the accelerated expansion of the universe, and supervoids might act as natural laboratories to study its effect. Observations of light from distant objects passing through supervoids have indicated the possibility of distortions in the cosmic microwave background and gravitational lensing effects, which can be used to explore the influence of dark energy on cosmic scales. Understanding how dark energy interacts with these supervoids can enrich our knowledge of the dynamics governing cosmic structure formation and expansion, giving us new insights into the great cosmic forces at play. And then there is the most perplexing anomaly of all, the cold spot in the cosmic microwave background radiation. This is a notable area that appears significantly cooler than the surrounding regions discovered through measurements taken by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft. This cold spot is unusual because it spans a substantial area of the sky, challenging the standard cosmological models that predict a more uniform temperature distribution across the cosmic microwave background. It is a bit like finding an unexpected cold patch in a perfectly warm room, and its existence begs for an explanation. One of the most intriguing aspects of the cold spot is its potential connection to the concept of other universes, or a multiverse theory. Some researchers postulate that the cold spot could be an imprint of a collision between our universe and another universe. According to this idea, if two universes were to collide, the interaction could create localized effects in the cosmic microwave background, resulting in temperature anomalies like the cold spot. This hypothesis suggests that we might be observing a remnant of a multiverse event, implying that our universe is not isolated, but potentially part of a broader fabric of realities. In addition to the multiverse theory, alternative explanations for the cold spot have also been proposed. Some scientists suggest it may be the result of a large-scale cosmic structure, such as a supervoid, that formed during the evolution of the universe. The cold spot could be a consequence of the Sachs-Wolf effect, where photons from the CMB lose energy as they climb out of the gravitational well of a large void appearing cooler. Other theories even point to potential systematic errors in measurement or the effects of foreground emissions from our own galaxy that could be masking the true nature of this anomaly. While the cold spot remains a subject of intense study and discussion, it serves as a vivid reminder of the complexities inherent in cosmology. Its implications extend far beyond our understanding of the cosmic microwave background, offering tantalizing possibilities about the existence of other universes and the interconnectedness of reality itself. This leads us to a concept that has sent ripples through the cosmological community: dark flow. This is a phenomenon that refers to the unexpected large-scale motion of galaxy clusters in a specific direction. This peculiar movement was first identified through measurements of the cosmic microwave background radiation, particularly by studying the motion of clusters away from the average distribution predicted by the standard model of cosmology. The observed motion suggests that these clusters are not merely expanding uniformly with the rest of the universe, but are instead being influenced by some gravitational pull from unseen structures beyond our observable universe. One potential explanation for dark flow points to the existence of massive structures that lie beyond the boundaries of what we can observe. These structures could include vast galaxy clusters or superclusters that exert gravitational forces strong enough to impact the motion of nearby galaxy clusters. Since these regions are out of our observational reach, they remain hidden from direct observation, making the gravitational influence we detect through dark flow a critical clue pointing toward their existence. The implications of dark flow extend into the realm of multiverse theory as well. If dark flow indicates that there are structures beyond our observable universe, it raises profound questions about the arrangement and nature of these regions. Some theories suggest that these unseen influences might even connect to other universes, hinting at a shared cosmic environment with different characteristics, densities, or principles of physics. Such interactions could potentially explain the large-scale motions observed and lead to greater insights about the overall topology of the cosmos. Studying dark flow presents both exciting possibilities and significant challenges for astronomers. It underscores the need for deeper investigations into the large-scale structure of the universe and the gravitational dynamics governing galaxy clusters as we continue to refine our methods and gather more data. Dark flow may unveil crucial information about the cosmic landscape, possibly leading to a better understanding of the nature of the universe and the enigmatic structures that lie beyond our correlative horizons. It is a mystery that reminds us that the universe is not just expanding, but is also being gently pulled and pushed by forces we cannot yet see, a great silent ballet of unseen giants. Let's now turn our gentle gaze towards another mind-bending possibility, the universe as a grand cosmic organism. This is a leap from the cold mechanical physics we've been exploring into a realm that blends science with a sense of the poetic and the profound. The idea that our universe could be a cosmic cell within a larger living superentity is a thought-provoking concept that invites us to contemplate the very nature of existence. This notion implies that our universe is not just a part of a grander structure, but that it also possesses characteristics similar to biological systems, suggesting a form of interconnectedness and hierarchy in the cosmos. Imagining our universe as a cosmic cell raises intriguing questions about the nature of life and consciousness on a universal scale. Just as biological cells are the fundamental building blocks of life, perhaps our universe serves as a fundamental unit of a more extensive sentient existence. This perspective encourages us to explore how the laws of physics and the principles governing the universe might reflect a comprehensive underlying order or purpose, a kind of cosmic DNA that guides its growth and evolution. Such a view could potentially merge concepts from both cosmology and biology, inviting a new dialogue around the implications of purposefulness in the cosmos. Furthermore, this idea could lead to the exploration of how interactions occur between different cosmic cells or universes. Just as biological cells communicate through chemical signals or electrical impulses, different universes might interact or influence one another in ways that we have yet to understand. Theories in physics, including those addressing quantum entanglement or parallel universes, could inform this exploration, suggesting that connections between our universe and others could exist within a meta-dimensional framework. The properties of dark matter and dark energy could even be seen as a kind of communication or energy transfer, a silent conversation between our universe and its cosmic neighbors. The observed acceleration of our universe's expansion could signify an awareness or adaptation mechanism, hinting at a dynamic, evolving cosmic system that is far more than the sum of its parts. This brings us to a beautiful metaphor for understanding the underlying frameworks that might govern various realities, cosmic DNA. Just as DNA carries the genetic instructions that determine the characteristics and functioning of living organisms, this idea suggests that there could be fundamental principles or codes that dictate the properties and laws of different universes in a multiverse. Cosmic DNA might represent a set of variables or constants that define the distinct characteristics of each universe. These variables could include the strength of fundamental forces, the masses of particles, and the nature of dark matter and dark energy. By elaborating on these underlying rules and initial conditions, cosmic DNA could provide a systematic way of describing how universes branch off or differ from one another. One way to approach the idea of cosmic DNA is through the lens of string theory and its multitude of solutions. In this framework, There is a wide variety of ways to compactify extra dimensions, each leading to its own configuration of physical laws and constants. In a sense, the different compactification schemes could be thought of as distinct cosmic genomes, with each scheme encoding a unique universe's behavior. The properties we observe in our universe, such as the values of physical constants, could be determined by the particular structure of this cosmic DNA, a unique set of instructions that gave rise to our reality. Another consideration lies in the potential role of quantum mechanics in shaping the cosmic DNA concept. Certain interpretations of quantum mechanics suggest that every quantum event creates branches of reality, leading to divergent outcomes across multiple universes. The rules governing these events and their interactions could form another layer of this cosmic DNA, where the nature of quantum phenomena dictates the evolution and properties of each universe in the multiverse. The idea of cosmic DNA invites us to contemplate how interactions might occur between different universes. If each universe encodes its own set of physical laws and unique traits, could there be pathways or connections facilitated by shared structures? This speculation echoes notions found in theories related to wormholes or higher dimensional pathways that connect universes, suggesting a more intricate web of relationships across the multiverse. Building on this idea of a living cosmos, let's explore the notion of cosmic respiration. This captivating concept suggests that universes undergo a rhythmic cycle of expansion and contraction, akin to the inhalation and exhalation of a living being. In a cosmic respiration model, the expansion phase could signify a period of energy dispersal and growth driven by the initial conditions of the Big Bang. During this phase, the universe stretches, galaxies move apart, and cosmic structures evolve. Conversely, the contraction phase could represent a time when gravitational forces begin to dominate, pulling all matter back together. This stage might lead to a big crunch, where the universe collapses into a singularity, possibly setting the stage for a new cycle. In this way, the universe could transition from an expansionary state back to a collapse state, resembling the exhalation process that expels air before drawing in a fresh breath again. The concept of cosmic respiration raises intriguing questions about time-space and the nature of existence itself. If multiple universes exist and follow similar cycles, it may imply that the life cycles of distinct universes are interconnected in some way. The rhythmic process may not only apply to our universe, but could also influence other realms within a broader multiverse framework, with cycles of expansion and contraction, leading to diverse properties and conditions in each universe. This model invites us to explore the roles of dark energy and dark matter in the cosmic respiration cycle, as understanding how these components influence the expansion and contraction dynamics could provide deeper insights into the underlying mechanics of the universe's life cycle. Finally, let us consider the idea of interuniversal synapses. This metaphor proposes a fascinating framework for understanding how communication or energy transfer might occur between different universes within a multiverse. Just as biological synapses facilitate communication between neurons, allowing information to flow within a complex nervous system, interuniversal synapses could serve as channels that enable interactions between distinct realities. One potential mechanism for these synapses is rooted in the idea of higher dimensions. Theoretical frameworks such as string theory propose the existence of additional dimensions that could allow for connections between parallel universes. These synapses might represent pathways or bridges that link higher dimensional structures, enabling matter information or energy to traverse between universes. These interuniversal synapses could manifest as gravitational or quantum entanglement links between particles or energy fields residing in different universes. If particle states are entangled across universes, interactions in one universe might influence corresponding states in another universe instantaneously. This could provide a mechanism for information exchange or coordination between systems that under classical physics would be completely isolated from one another. Additionally, the notion of interuniversal synapses could involve exotic forms of matter or energy hypothetical particles that may not exist in our universe, but instead reside in others. These particles could facilitate energy transfer across the multiverse, perhaps enabling the sharing of resources or physical properties. The study of such interuniversal connections could also lead to intriguing discussions about the implications for cosmological principles like the conservation of energy and information. If communication and energy transfer were possible between universes, it might modify our understanding of how these laws operate when considering a broader multiverse context. Let's now consider some of the more abstract yet profoundly beautiful ideas that blur the lines between cosmology, quantum mechanics, and philosophy. We've explored the universe as a physical space, but what if reality itself is a construct, a story told in a different language? This is the realm of the simulation hypothesis, a thought-provoking concept that posits that our reality, including the physical universe and everything within it, might be an artificial simulation akin to a highly advanced computer program. This intriguing idea suggests that a sufficiently advanced civilization, a kind of cosmic programmer, could create realistic simulations of their predecessors or entirely different worlds, leading to the possibility that we are currently living in one of these simulations. This concept has gained traction in popular culture and philosophical discourse, particularly in light of our own rapid advancements in technology and virtual reality. One of the key arguments supporting the simulation hypothesis is based on the idea of probability. If it is feasible for advanced civilizations to create numerous simulations, then the number of simulated realities could far outnumber the one original or base reality. This suggests that the beings living within these simulations would greatly outnumber those in the original universe. Consequently, the likelihood that we are in the original reality becomes increasingly diminished, leading to the conclusion that we might indeed be part of a simulation. This hypothesis can also be linked to the framework of a multiverse. If our universe is just one of many simulations created by advanced beings, it implies a vast multiverse landscape where countless variations of realities exist. Each simulation could run with distinct physical laws, cultural histories, or even evolutionary paths, resulting in a plethora of possible universes that diverge from our own. In this context, the term multiverse expands beyond the traditional interpretations in cosmology, where multiple universes arise from different cosmological events, to include those generated through intelligent design. Exploring the simulation hypothesis encourages us to rethink fundamental questions about existence, consciousness, and reality. If our understanding of physics and the universe is merely a subset of a more profound simulation, it raises questions about the underlying purpose of these simulated realities and the nature of the beings that create them. As scientists, philosophers, and technologists delve into this captivating subject, the simulation hypothesis serves as a bridge between advanced technology, theoretical physics, and the contemplation of our place in the broader multiverse, illustrating how deeply interconnected these concepts can be. It is a quiet thought to hold that the stars we see twinkling in the night sky might be lines of code, and the gentle whisper of the wind a sophisticated algorithm. This brings us to a poetic and evocative idea. What if the mystery of dark energy, the force that drives the accelerated expansion of the universe, is not a force at all, but a sign of something more profound? The concept that our universe could be digested by a larger cosmic organism presents a fascinating and imaginative framework for understanding the cosmos's dynamics. Dark energy is currently recognized as the mysterious force that accounts for about 70% of the universe's total energy density. This conceptualization suggests that rather than being a mere force or constant dark energy, could be a sign of something more profound and interconnected with a larger living entity. If we were to consider the possibility that our universe is a part of a cosmic organism, it raises intriguing questions about what it means for one universe to engage in such a biological process. In this scenario, the accelerated expansion driven by dark energy might be akin to metabolic processes where the universe is being transformed or utilized by a larger cosmic structure. This might imply that as our universe expands, it is releasing energy or information into this greater being, effectively becoming part of a broader system that influences not only itself, but other regions or entities as well. This metaphorical digestion could also explore relationships between different parts of the cosmic environment. Just as biological systems maintain a delicate balance, a cosmic organism might oversee the balance and interactions between various universes or cosmic structures. The properties of dark energy as they influence the expansion rate may indicate a mechanism by which energy circulates or is exchanged with the larger entity, suggesting a dynamic interdependent relationship rather than an isolated existence. This idea challenges our current understanding of dark energy and the universe's ultimate fate. The notion that our universe might be alive in some sense posits that cosmic evolution may involve more than just physical processes, introducing the idea of purpose, intentionality, or even conscious influence in cosmic dynamics. If dark energy is a byproduct of a larger organism's interaction with our universe, it could imply that the universe's expansion is part of a grander strategy for growth, evolution, or maintenance of balance in a cosmic ecosystem. Ultimately, while the notion of our universe being digested by a larger cosmic organism is speculative, it invites rich philosophical and scientific discussions about the nature of existence and the interconnectedness of all things in the cosmos. Such a perspective could inspire new lines of inquiry into what cosmology and biology might share at deeper levels, prompting us to rethink the conventional boundaries that separate life energy and the universe itself. Now let's explore a concept that takes us back to the roots of quantum mechanics and its strange, beautiful dance with reality probability waves. This idea is closely tied to the idea of the multiverse, where particles do not have definite positions, but instead exist as probabilities described by wave functions. These probability waves can span across space and time, suggesting the potential for various outcomes and states to coexist until an observation collapses the wave function into a definite result. When considering the edge of our universe, or the boundary of our observable cosmic horizon, the notion of probability waves becomes particularly intriguing in its implications for the formation of new realities or universes. At the edge of our universe, these probability waves could represent the uncertainty inherent in quantum phenomena, allowing for fluctuations that could give rise to new configurations of matter and energy under specific conditions. This idea aligns with theories of cosmic inflation, which suggests that tiny quantum fluctuations in the early universe led to the large-scale structure we now observe. If such probability waves can create diverse regions of space with distinct properties, it raises the possibility that they could initiate processes that generate entirely new realities or pockets of existence. These probability waves might also suggest mechanisms for the emergence of parallel universes, as described in many worlds' interpretations of quantum mechanics. In this framework, every quantum event produces a branching reality in which every potential outcome occurs in its own distinct universe. If the edges of our universe are suffused with probability waves, the interactions and collapses of these waves may lead to the creation of new branches, fostering the existence of alternative realities that develop based on different paths of quantum events. Furthermore, the dynamics of probability waves could influence how components of our universe interact with hypothetical structures or realms beyond our observable limits. For instance, if probability waves extend from our universe to areas that are not directly observable to us, they may establish connections that facilitate the exchange of energy information or even matter with other realities. Such interactions could play a role in the evolution of these new realities, perhaps allowing them to draw on the foundational properties of our universe while also developing unique characteristics of their own. As researchers continue to explore the foundational aspects of quantum mechanics and cosmology, the study of probability waves at the edges of our universe could yield profound insights into the complex relationships between different realities. This exploration not only challenges our understanding of the nature of reality, but also invites contemplation about the interconnectedness of all existence, potentially expanding our view of the universe and the myriad possibilities that may spring from its inherent uncertainties. Let's now consider how these seemingly abstract ideas might be woven together into one grand unified picture. This brings us back to the holographic principle, but this time we will see it not just as a theory of black holes, but as a potential blueprint for a cosmic hologram. This is the idea that our universe, with all its galaxies, stars, and planets, is simply a projection from a higher dimensional reality. Imagine looking at a two-dimensional image that, when viewed from a certain angle, seems to pop out in 3 dimensions. The holographic principle suggests that our 3-dimensional reality might be just such a phenomenon, with the real information residing in a lower dimensional, more fundamental realm. In this framework, the very laws of physics and the constants that govern our universe could be reflections of deeper underlying principles in a higher dimensional space. This could lead to a re-evaluation of fundamental concepts such as time-space and even causality, as they might be emergent properties rather than fundamental aspects of existence. For instance, the nature of dark matter and dark energy could be reconsidered in this context, as they may be manifestations of higher dimensional effects rather than independent entities within our universe. This transforms the quest for understanding them from merely identifying particles or fields to exploring the deeper geometric and informational fabric of the universe that encodes and manifests these elusive phenomena. The synchronicity of information encoding in a holographic universe could also have profound implications for our understanding of black holes and entropy. The work of physicists like Jacob Bekenstein and Stephen Hawking suggested that the information content of a black hole is proportional to its surface area, aligning beautifully with the holographic principle. This invites deeper inquiries into how information energy and the fundamental nature of black holes intersect with the broader cosmos. If our universe is indeed a holographic projection, then perhaps black holes are not simply cosmic devourers, but rather a kind of cosmic projector taking in information and then projecting it out onto the 2-dimensional surface of the universe, a silent and continuous act of creation and recreation. Finally, we arrive at the beautiful, poetic, and chaotic idea of quantum foam wormholes, but we will now see them as the very stitches and seams of this holographic quilt. At the intersection of quantum mechanics and general relativity at the smallest possible scales, space-time is not a smooth, continuous fabric. Instead, it exhibits a frothy, fluctuating structure, a turbulent sea of virtual particles and fields that constantly pop in and out of existence. This chaotic, ever-changing medium, the quantum foam, is the underlying reality that gives rise to the smooth, elegant universe we perceive on a larger scale. Within this restless, churning foam, tiny connections or tunnels might spontaneously appear and disappear, linking different points in our universe, or even different universes altogether. These are the quantum foam wormholes, the ephemeral, fleeting bridges that connect all of reality. The chaotic nature of quantum foam could mean that while these connections are fleeting, they could still have significant effects on the dynamics of the universes involved. They are a constant restless hum in the fabric of reality, a perpetual churning that might be the source of new realities. The existence of these wormholes would suggest that the behavior of particles is not entirely limited to our familiar 3-dimensional space, but could entail complex interactions with higher dimensional structures or neighboring universes. This is a universe that is not static and isolated, but one that is constantly in flux, connected to a vast, unseen network of possibilities. The idea of quantum foam wormholes connecting our universe to others at the smallest scales presents an exciting frontier in theoretical physics, and it is a beautiful, gentle thought to hold as we drift off to sleep. We are not just a part of one universe, but a part of a great cosmic foam, a vast interconnected tapestry of existence that stretches beyond our single isolated reality. We are the stitches and seams, the bubbles and the foam of a cosmos that is far stranger and more beautiful than we can possibly imagine. And so we arrive at the final chapter of our quiet cosmic journey, a gentle contemplation of where all these magnificent ideas might lead. We've floated through the vastness of our observable universe, imagined the great stretch of inflation, and pondered the ghostly forces that push and pull on the cosmic fabric. We've dared to dream of a multiverse, a cosmic tapestry of endless possibilities, and we've peered into the strange geometries of space-time itself. Now, as our minds begin to settle, let us look forward to the gentle, unwritten future of our exploration. The quest to understand the universe's boundaries and its grander structure is not a solitary pursuit. It is an intricate dance of theory and observation, and it is here that the future holds its greatest promise. Future space-based telescopes and observatories hold immense potential for expanding our understanding. By positioning these advanced instruments outside Earth's atmosphere, scientists can overcome many limitations imposed by our own sky, allowing for clearer and more detailed observations of distant, ancient cosmic phenomena. These telescopes operating across a wider range of wavelengths will be like a new pair of eyes for humanity eyes that can see not just the visible light, but also the invisible cosmic glow that tells us so much about the universe's history. One key area where these future observatories could improve our understanding is in the study of distant galaxies and the large-scale structure of the universe. Telescopes equipped to capture infrared, ultraviolet, and even sub-millimeter wavelengths will enable astronomers to detect light from the earliest stars and galaxies that formed after the Big Bang. By examining these most distant celestial bodies, researchers can trace the evolution of the universe, better understand its expansion history, and investigate the formation of cosmic structures that lie at the very edge of our observable sphere. It will be like finding the first pages of a book we are already reading, shedding light on the story's beginnings. Additionally, advanced telescopes will enhance the study of dark matter and dark energy, those two enigmatic components that hold the fate of the cosmos in their hands. Instruments designed to map the subtle gravitational effects of dark matter and measure the universe's expansion rate with unprecedented precision can provide crucial insights into these phenomena. By characterizing these unseen elements, scientists could refine our models of cosmic growth and ultimately extend our understanding of structures and influences located beyond our observable limits. It is in this way that the invisible might become a little more known. Beyond merely observing the known universe, future observatories may also facilitate the study of the cosmic microwave background, CMB radiation, in greater detail. Increased precision in mapping its tiny temperature fluctuations can provide information on the early universe's conditions and potentially reveal anomalies that hint at structures lying beyond the observable limits. As these technologies are developed, they will empower researchers to not only gaze deeper into the cosmos, but also to confront the fundamental questions of existence concerning the universe's boundaries and its larger structure. This brings us to the next great partner in our cosmic journey: artificial intelligence. AI is poised to play a transformative role in developing and testing theories about what lies beyond our universe, particularly by enhancing data analysis simulations and theoretical modeling. As the volume of astronomical data continues to grow exponentially, AI techniques can assist researchers in efficiently processing vast data sets, identifying patterns, and deriving insights that may not be easily detectable through conventional methods. It's like having a cosmic detective who can sift through billions of clues in a fraction of a second, finding a trail that we might have missed entirely. One major application of AI lies in the analysis of data from telescopes and observatories. Machine learning algorithms can be trained to detect subtle signals or anomalies within the cosmic noise, helping astronomers distinguish between genuine astrophysical events and spurious data. For example, AI could analyze the cosmic microwave background radiation to identify irregularities or anomalies that might suggest influences from realms beyond our observable universe, a kind of cosmic fingerprint left by a passing neighbor. AI can also enhance the modeling of complex physical systems and the simulations used to explore theoretical predictions in cosmology and particle physics. This predictive power can inform tests of existing theories while generating new hypotheses regarding what might exist beyond the observable cosmos. The integration of artificial intelligence into astrophysics and cosmology holds the promise of significantly advancing our understanding of the universe and its underlying structures. As AI tools continue to develop and mature, they will likely provide valuable resources that deepen our exploration of the cosmos, leading to breakthroughs in how we perceive reality and the possible connections we might uncover beyond our observable universe. Finally, we must not forget the powerful engines of discovery right here on Earth: particle physics experiments. The advancements achieved at facilities like the Large Hadron Collider have the potential to significantly enhance our understanding of multiple universes. By probing fundamental questions about the nature of matter, energy, and the forces that govern the cosmos. As researchers conduct high-energy collisions at the Large Hadron Collider, they explore the behavior of subatomic particles under conditions that mimic those present shortly after the Big Bang. This experimental approach not only provides insights into the fundamental building blocks of our universe, but also delves into theories that suggest the existence of multiple universes. One potential contribution of the Large Hadron Collider to the multiverse concept lies in the search for new particles and interactions predicted by extensions of our standard model of physics. For instance, certain theories such as supersymmetry or string theory imply a richer tapestry of particles than those currently known. Discovering these new particles could provide evidence for the multiple dimensions and energy states associated with multiverse theories. If researchers detect phenomena like extra dimensions or previously unknown particles, it could support the idea that our universe is connected to others in a more intricate, multidimensional framework. The exploration of the Higgs boson's properties, for example, could shed light on the mechanism of cosmic inflation and early rapid expansion, thought to set the stage for our universe's structure. If inflation can be linked to a broader theory that includes multiple universes, then enhancements in our understanding of the Higgs boson could also open avenues for exploring those connections. The work conducted at particle physics facilities is invaluable in expanding our knowledge of fundamental principles governing the universe. As scientists continue to decipher the intricacies of particle interactions, they pave the way for a deeper understanding of the multiverse, potentially revealing connections to alternate realities and reshaping our comprehension of the cosmos as a whole. And so we come to the end of our quiet journey, a journey not of miles, but of ideas. We have stared into the great unknown and allowed our minds to stretch, to wander, and to wonder. We have not found all the answers, and in fact, we have found more questions than we began with. But perhaps that is the point. The beauty of science and of our own human curiosity is not in the destination, but in the journey itself. The universe is a vast, quiet, and beautiful mystery, and we are its gentle, persistent explorers. We may never know what lies beyond the boundaries of our known universe, but the very act of asking the question, of imagining the possibilities, and of reaching out into the dark, silent sea of space is what makes us truly alive. As we close our eyes, let us hold on to this feeling of wonder, this peaceful, humbling awe in the face of the great cosmic unknown. The universe is far stranger and more beautiful than we can possibly imagine, and that in and of itself is the most comforting and magnificent truth of all.